Alright guys, welcome back. We're going to start covering this last section, so the last bit of material you'll be responsible for. So if you remember from last class, we talked about dependent and independent and dependent variables. We talked about how values for the dependent variable literally depend on the value of the independent variable. And we talked about functions, that relationship, and how functions can be, or that function relationship can be illustrated using a table, graphically, and even by way of an equation. Okay, and that's actually what we're going to focus on today. We're going to look at something called linear modeling. So we're going to come up with we're going to look at equations that represent that relationship between our independent variable, or our x, and our dependent variable, namely our y. Okay? Alright, so we'll get started. We have seen the graphs of linear functions before. If you think back to 8a, when there was an example in there of the population of a town that was growing linearly, so it literally was a straight line. And the reason is because the rate of growth is unchanging. It's fixed every single year. Okay. So yeah, a linear function is going to have a constant rate of change, and graphically it's going to be a straight line. And the rate of change is equal to what we refer to in algebra as the slope. Okay, you guys may remember from your high school, perhaps, rise over run. Okay, what this rise means is the change in your dependent variable divided by the change in your independent variable. Okay, and we're going to see well, I've got it right here, see, in the notes. And then the greater the rate of change, the steeper the slope, or the greater the slope. In other words, the steeper the line is going to be. Okay? And you can have both positive and negative slope, or positive and negative rates of change. We saw this in 8a. When the rate of change is positive, we have growth, and we'll have a line going uphill. When the rate of change is negative, then you have a decaying process, and the line would be going downhill. Okay, and it's possible to also have a slope of 0, which would give you a horizontal line. All right, and we can calculate that rate of change by finding the slope between any 2 points on the graph. So this just means that if you have a function, a linear function that's graphed, you can pick any 2 points, find their associated coordinates, and you can figure out what the change in your y is divided by your change in your x's. Okay, that's what this is telling us right here. So here's an example. Okay, so let's say we've got this line. This represents some relationship between our independent variable and our dependent variable, whatever those are. And so from point 1, so we've just picked 2 arbitrary points here, point 1 and point 2. So the vertical distance between these 2 points, this is the change in the dependent variable, okay? Or otherwise, it's the change in the y values, y coordinates of those 2 points. And this is also why for the slope formula, that they say rise over run, okay? Because this is vertical change here, and then the change in the 2 x coordinates of these points is going to give you the change in your independent variable, or your change in your x coordinates, also referred to as run, okay? All right, so we're going to take this idea or this concept and kind of apply it. Let's look at this next slide. Finding your rate of pay, okay? So we're trying to find a rate here. So let's say you get paid an hourly wage. After working 2 hours, you would get paid $30. So guys, that essentially is one of my ordered pairs, okay? 2 hours corresponds to $30. In other words, we have these two variables here. The number of hours you work, that is your independent variable. We'll use a capital H to represent it. And the number of dollars that you earn, given that specific number of hours, is your dependent variable, okay? And you guys know this intuitively. Your paycheck depends on how much time you work, right? If you get paid by an hour. So this could be like our first data point. And then furthermore it says after working 6 hours, you would make $90. Okay, so this is like our second data point. 6 hours corresponds to $90. And so the question is, what is your rate of pay? Okay, so to find this, the rate of pay is going to be equal to the difference in our dependent variables divided by the difference in our independent variables. Okay, so if you want to think about these as like x and y's, that's fine. Some people will even further designate them as x1, y1, and x2, y2, just to illustrate that these are the x and y coordinates of your first point. These are the x and y coordinates of your second point. Okay. So the change in your dependent variable means you're going to take y2 and subtract from it y1. Okay. Or in other words, you're finding the difference in those two dependent variables. And then you're going to divide this by the change in your independent variables. So in other words, x2 minus x1. And this is a very common formula used in algebra. Okay. And so if we plug our numbers in here, guys, $90 for y2 minus y1, which is $30. This will give us our change in the dependent variable. And then x2 is 6 hours minus x1 is 2 hours. This will give us our change in our independent variable, or change in time. Okay, so 90 minus 30 is $60. So that's a difference of $60 over a difference of 4 hours. And if these will divide out, go ahead and divide them out. 60 divided by 4 is 15. So we end up with $15 per hour. Okay, and the units do matter here, by the way. So that is your rate of pay. All right, let's look at another example here. So this says this is a price demand function. So you guys remember, we've talked about this previously. That is, the price of a good increases, the demand will decrease, and vice versa. Okay, so a small store sells fresh pineapples. Based on data for pineapple prices between $2 and $5, the store owners created a model in which a linear function is used to describe how the demand, the number of pineapples sold per day, varies with the price. Okay, so for example, this point, $2 and 80 pineapples, means that when a pineapple costs $2, you can expect to sell 80 of them. And so the question is, what is the rate of change for this function? Well, we actually need a little bit more information. They didn't actually. So at $2 we can sell 80. We need to know how many we could sell at $5. Okay, and that information is down here, guys. Okay, so at $2 we would sell 80 pineapples because they're cheaper. But if we raise the price to $5, we can only expect to sell 50. And what they've done, and I'll zoom in here for you to see, is they've actually plotted these 2 points, okay? So the horizontal axis represents values of our independent variable, price, and the vertical axis represents values of our dependent variable, namely number of pineapples sold, okay? So when you price your pineapples for $2, you can sell 80 of them. And then when you price them at $5, you can only sell 50 of them. Okay, so with these 2 points, we can kind of draw this line through there. And so this line is a model. It represents how the change in price will affect the change in number of pineapples sold. And so you can see way out here, if you raise the price to $9 a pineapple, you might only be able to sell 10 of them. And then if this model is accurate, then over here when you raise your price to $10, you're not going to be able to sell any. Nobody's going to buy them. It's just too high. And then on the other side, if you decrease your price to say $1, you're going to be able to sell 10 more pineapples. Okay. All right, so the change in price, which is the independent variable, okay, was just $5 minus $2. And that will give us $3. Okay. So we've increased the price from 2 to 3, but the number of pineapples has actually decreased. Okay, so the change in demand, or the change in pineapples, is going to be 50 minus 80, and you are going to get a negative number here, negative 30. Now, in the context of this problem, what this means is that when you increase the price by $3, you can expect to sell 30 fewer pineapples. Okay. And notice too, guys, how I did these. I always started with my second point. I said 5 minus 2, and then I said 50 minus 80. You have to be consistent here. All right. Now, if we want to actually find the rate of change, it's going to be the change in our dependent variable, which is negative 30. I didn't put a dollar sign. Oh, wait, no, I don't need a dollar sign. Yeah, it's pineapples. Okay, that's the unit. Okay, so the change in our dependent variable, well, the number of pineapples sold is decreasing. Okay, over. The difference in price is $3. Okay, and so when we divide these out, 30 divided by 3 is 10. And a negative divided by a positive is a negative. So we get negative 10 pineapples per $1. Oh, well, I put that dollar sign in the wrong spot. Negative 10 pineapples per $1. Okay, so this just means that the price, or the number of pineapples sold, will decrease by 10 for each $1 that you raise the price. Okay, but anyway, that is the rate of change. So as the price increases, the number of pineapples is going to decrease by 10 per $1. Okay. Okay, let's look at another example of a function. This relationship between time and rainfall amount. Okay. Now, for this to actually work, guys, we have to assume that the rain is constant. Okay, so the rate of rain is never changing. Of course, we know that in reality that's seldom the case, right? Normally it may start out raining really hard and then start to taper off, but very seldom does it rain at the same rate for hours and hours and hours. But we're going to assume that it does, okay? And so what we have here is a graph of how these two variables are related. So the longer it rains, and you can see this line going uphill, then the greater the depth of rainfall, okay? And so you can see after, if it rains for 1 hour, this point right here corresponds to 2 inches. So that means after 1 hour, you've received 2 inches of rain. And over here, after another hour, then the depth in rainfall has gone up to 4 inches. Okay, so when it asks us to find the slope of this function, all we need to do is just pick 2 points that are on this line. Go ahead and write down the coordinates. Okay, so hours comes first. That's like our x, basically. 2 hours corresponds to 4 inches of rainfall. So this is kind of like our x1, and this is like our, I like to do the leftmost point as my first point, and the rightmost is my second. So this would be like x2, y2. And then the coordinates of this point here, 1 hour corresponds to 2 inches of rain. So this is like my x1 and my y1. Okay. So to find the rate, you can just use that formula again. y2 minus y1 divided by x2 minus x1. Okay. So I come to my second point. My y-coordinate, or the value of my dependent variable, is 4 inches, minus the value of the dependent variable for my first point is 2 inches, so 4 inches minus 2 inches. That's going to give us a difference of 2 inches in rainfall. And then the difference in time from our second point and our first point is just 2 and 1. Okay, so 2 hours minus 1 hour is 1 hour. And so the rate of change, or the slope of this line, which is the same thing, is 2 over 1, or in other words, 2 inches per hour. So that's the rate at which it's raining. And I don't know how much you guys keep up with. Whoops, my computer froze again. Yeah, if you keep up with meteorology, 2 inches an hour is a significant amount of rainfall. I remember, let's see, it was last year, when one of the remnants of one of those hurricanes, I think it was the first one, the one that went through Texas first and then came over to Arkansas. I can't remember the name of it, but anyway, it doesn't matter. That was some of the heaviest rainfall that we got. In fact, I remember one of the meteorologists saying that it rained an inch in like 10 minutes. And so that would be equivalent to 6 inches per hour. That's about as heavy as it ever rains. One of those tropical systems like that, those huge low pressure systems. But anyway, all right, we'll continue. Okay. So now we're going to talk about this rate of change rule. So what we're doing here, guys, is if we know the rate of change, then we can make predictions. Okay, so for example, think back to this one. If I know that the rate at which it's raining is 2 inches per hour, then I can tell you how much it's rained if you tell me how many hours that it's rained. So for example, if it's rained 5 hours, then 5 times 2 inches an hour is 10 inches. Okay? So that's what we're going to look at now. So the change in the dependent variable, so think about rainfall, is equal to the rate times the number of hours, or in other words, the change in the independent variable. Okay? This could also be like your rate of change is here, and this could be the price for a pineapple, and over here will be the number of pineapples that you can expect to sell. So once we know that rate of change, then we can use that as a model to model what a future value for our dependent variable might be. Now this is also sometimes written as y equals nx, okay, where x just represents our independent variable. Okay, we talked about that. And y represents values of our dependent variable. And then m in algebra is used to denote the slope, which is the same thing as the rate of change. Okay? It's easier to write it this way, guys, instead of having to write out all these words. Okay? Y equals mx, where the value of y is equal to the rate times the value of x. All right, let's continue here. So it says, using the linear demand function from above, the one we were talking about with those pineapples, predict the change in demand for pineapples if the price increases by $3. Okay. So the rate of change, we figured that one out. It was negative 10 pineapples per dollar. If you guys remember that. Negative 10 pineapples per dollar. Okay, so that's the rate. So that's what I'm going to put down here. Now down here, you don't necessarily have to write all the units. The units will cancel out and leave you with the desired unit. Okay. Times, and I don't even like to use that x. Okay. That's why we get away from using x to denote multiplication. I'm going to use the dot to denote multiplication. The change in price. So if the price increases by $3, and that's what I put in here, okay, $3. Oh, the computer froze again. Okay, there we go. Okay, so I've got the rate of change in here. We've got the change in the price, which was our independent variable. And if we multiply these two, this will give us our change in our dependent variable, which is the number of pineapples sold. I'm going to stop this video after this slide. My computer keeps freezing. Alright, well, negative 10, guys, times $3 is negative 30. And notice one thing, the dollar signs would divide out and leave you with just pineapples, and that's the unit that we're looking for. So this would end up being equal to negative, negative 30 pineapples. Okay. So all this means here is it allows you to see how a change in price is going to affect a change in demand. So we can see that if we increase the price by $3, then we're going to sell 30 less pineapples. All right. I think I'll go ahead and do this one, and then we may call it stops for this video. Okay, so we want to predict total pay. Okay, so we're going to use the rate of pay example from above to predict how much we would make if we worked 12 hours. Well, if you guys remember that, we calculated that rate of pay because I can recall, I think 6 hours resulted in $90, and then 2 hours resulted in $30. Okay. And we used that slope formula, and we found that the rate was $15 per hour. Okay. So I want to use that same formula right here. Although, right up here, I'm going to write it as y equals mx, because I don't want to have to write change independent variable is equal to rate of change times change in independent variable. Okay. Alright, so y, which is the predicted value, is equal to the rate of change times the change in our independent variable. Alright, so our independent variable is the number of hours worked. So if I plug a 12 in for x, and I plug $15 an hour in for m, $15 per hour times 12 hours, you could see that the units hours will cancel, and this is going to leave us with 12 times 100, 12 times $15, which is going to leave us with dollars. And I believe that that is $180. Okay, so that would be the predicted earnings after working 12 hours. So hopefully you can kind of see that once we know the rate, then we can make predictions. Okay. All right, so I think we'll stop this one here, guys, and we'll pick up with this next example. Okay.